Hi everybody, in this video we're going to be talking about the beginning of chapter 1, which talks about expressions and equations. So let's start off with some vocabulary. So a variable is a letter or symbol that's used to represent a value that can change. So this can be any letter from the alphabet. And occasionally we will use symbols as well. Now a constant is just a number or value that does not change. So here's some examples of constants. And a numerical expression contains constants and operations. So basically just combinations of numbers. There are no variables in a numerical expression. So this would be something like 2 plus 3, 4 minus 5, negative 2 times 6. Those would all be numerical expressions. An algebraic expression contains variables, constants, and operations. So this would be something like plus 1, 2y minus 3, 4z minus 2w. Those would all be algebraic expressions because they contain variables, constants, and operations. Okay. Notice the and or here. Okay, it doesn't have to have an operation like a plus sign or a minus sign. It would be something like 5 would be 5 times x. Now, when we're looking at expressions, we want to know what words are associated with which operations. So you can see that the plus sign, okay, you know to use a plus sign if you see words like increased, sum, plus. Use a minus sign if you see you're taking the difference or something is less than something else. And you're going to see times, the product of, and then with division, you'll typically see divided by or quotient. Okay, so for each of these examples, we're going to write out in words what this expression is telling us. Okay, so if you look at example A, we have x plus 3. Okay, one way to write that out in words would be x plus 3. Okay, pretty simple. Another way, okay, if you look at the red plus sign here, another way would be to say the sum. So we could say that x plus 3 is the sum of x and 3. Okay, at this point, I want you to pause the video, and I want you to try examples B, C, and D. All right, for example B, we have m minus 7. So that'll be our first way to write it. Another way could be to say m minus 7 is 7 less than m. Now, it's really important to know that we couldn't say m less than 7. That would be something different. M minus 7 has to be 7 less than m, not the other way around. Example C, we have 2 times y. We could also say that that is the product of 2 and y. And lastly, example D, we have k divided by 5. We could also say that it is the quotient of k and 5. So in these examples, we took an algebraic expression and we were turning it into words. We were writing it out as a short statement. So the other thing we want to be able to do is go the other way. We want to be able to take words Okay, take it and turn it into an algebraic expression. Later on in the year, we'll make equations and use those to solve problems. So example A says Eve reads 25 pages per hour. Okay, I'm going to give you a tip here. Anytime you see per, that means we're going to have multiplication involved. So we want to write an expression for the number of pages she reads in H hours. Important thing to notice here is it's telling us what variable we should use. So if she's reading 25 pages per hour, and we use H to represent hours, our expression is going to be 25 times H, which is the same as just 25H. That would represent how many pages she can read in H number of hours. If she reads for 1 hour, it's just going to be 25 times 1, means that she would just read 25 pages. If she reads for 2 hours, now we have 25 times 2, so she'll read a total of 50 pages. Go ahead and pause and try example B. In example B, it says Sam is 2 years younger than Sue. Okay, that probably means that we're going to be using subtraction because Sam is younger. They also tell us what variable we're going to use. Okay, it tells us that Sue is Y years old. So if Sue is Y years old and Sam is 2 years younger than her, that means Sam's age must be Sue's age, which is Y, minus 2. Now let's talk about evaluating algebraic expressions. Okay, whenever we evaluate an expression, it means that we want to find its value. Evaluate an algebraic expression, we're going to, okay, and substitute really means replace the numbers in for the variables. Okay, so we're going to plug in a number for the variable, and then we're going to use our order of operations to find its value. So for each of these examples, we're going to be using an x value of 8, a y value of 5, and a z value of 4. So in example A, if I want to find x plus y, I'm going to take what x is equal to, which is 8. I'm going to take what y is equal to, which is 5, and I'm going to add them together. So using our order of operations, we can find that x plus y is equal to 13. Now this only works if they tell you what x, y, and z are equal to. If we just had x plus y but we didn't know what x and y were, we wouldn't be able to evaluate the expression. All right, let's try B. B says we're going to take y and divide it by z. So we take 5, which is what y is equal to. We're going to divide it by 4, which is what z is equal to. And in this case, we're just going to leave our answer like this. Okay, 5/4 is our answer, and the fraction cannot be reduced. Please leave your answer as a fraction, not a decimal. Go ahead and try examples C and D. All right, in example C, we're doing x times y. So x is 8, it's 5. There is no operation between x and y, so that means that they're being multiplied. So 8 times 5 gives us 40. For example D, we're doing z minus x. So we do 4 minus 8, which gives us -4. All right, so this is evaluating. We start with an expression, we plug in numbers for the variables, and we use our order of operations to find the value of that expression. So let's talk about solving. Now, an equation is a mathematical statement that shows that two expressions are equal to each other. So you have one expression equal to another expression. A solution of an equation is a value of the variable that makes the equation true. So we're trying to find what number do I need to plug in for my variable to make it so that the left side of my equation is equal to the right side of my equation. So a couple key ideas to follow here. When we're finding solutions, you have to isolate the variable first. That means get it by itself. Get it. You want it to be the only thing on that side of the equation. So to do this, we're going to use something that we call inverse operations. Inverse operations are operations that undo each other. Okay, so for example, addition and subtraction are inverse operations. Multiplication and division are inverse operations. And remember, when we're solving equations, it's really important that we keep the equations balanced. Okay, in order to do that, you have to perform the same operations on both sides. So whatever you do to one side, you must do to the other. If I add 2 to one side of my equation, I have to add 2 to the other side as well. So let's see some examples. In example A, we have x minus 10 is equal to 4. Now, I'm going to do something here. I'm going to draw a line underneath my equal side so that we can cut this equation into two halves, two sides. We have a left side and a right side. Remember, when we're solving, our goal is to get our variable, which in this case is x, all by itself. Now on the left side right now, we have x minus 10. So to get x by itself, we need to get rid of that minus 10. So we're going to use inverse operations. If a minus 10, I need to add 10 to both sides. Because if I add 10 to negative 10, these are going to cancel out, leaving me with just x on the left side of my equation. Now, we have to keep it balanced, so if I'm adding 10 to the left side, I also have to add 10 to the right side. My equal sign stays on that red line, so I get x is equal to 4 plus 10, which is 14. Now, I talked about a solution being the number that makes the equation true. So what that means is, if I took 14 and plugged it back into the x in the original equation, that value of 14 is what makes this equation true. Because if we look on the left side, 14 minus 10 is really 4, which gives us 4 equals 4, which is true. It makes the left side equal to the right side. So the answer to our equation here, the solution, is x equals 14. Okay, let's look at example B. Very similar. We're going to cut it in half into a left side and a right side. We're going to isolate our variable x. Right now we have x minus 1, so we need to add 1 to both sides to get x by itself. The minus 1 and plus 1 cancel each other out, leaving us with just x. 5 plus 1 gives us 6, which is our solution. Go ahead and try examples C through F. All right, in example C, we want to get x by itself. We have a plus 2, so we need to subtract 2 from each side to get x by itself. The plus 2 and minus 2 cancel each other out, leaving us with just x on the left side. Negative 1 minus 2 gives us negative 3, which is our solution. Remember, when we're working with negative numbers, I'm going to draw a number line here. Okay, if I started at negative 1, if I start at negative 1 and I'm subtracting 2, that means I'm going to go left 2, which has me land at negative 3. All right, for D, we want to isolate x, so we need to subtract 12 from each side. These cancel. We're left with x is equal to 8. Now, example E and F, it got a little trickier because the order of the number in the variable on the left side switches. Negative 8 plus b is the same as a minus 8. If I make that small change, now I can see it's just like my previous problems. I'm going to split it down the middle. To get b by itself, I'm going to add 8 to both sides. These cancel, and I'm left with b is equal to 10. Same thing for example F. Negative 11 plus z is the same as a positive z minus 11. So now I can split it into two sides. I'm isolating z, so I'm going to add 11 to each side, leaving me with z is equal to 44. So these equations that we just saw all used addition and subtraction. So let's look at some that use multiplication and division. For example A, our variable is on the right side instead of the left side, but there's nothing wrong with that. That is totally fine. We're still going to split it into two sides. Now we're trying to get k by itself still. Right now, k is being divided by a negative 5. So the inverse of division is multiplication. So what we want to do is we want to multiply both sides by negative 5. Because if I multiply the right side by negative 5, what's going to happen is these are going to cancel each other out, leaving me with just k. And on the left side, I'm doing negative 4 times negative 5. Remember, when we multiply two negative numbers, we get a positive. So we get k is equal to positive 20. Very similar idea for b. We have m divided by 3. To get m by itself, we need to multiply side by 3. So these cancel. We're left with m on the left side. 1.5 times 3 gives us 4.5. Leave this one as a decimal, only because the right side of our equation started off as a decimal. Now C and D, what we have are multiplication occurring between a number and a variable. So the inverse of multiplication is division. So if I want to get x by itself, well, 7 is multiplying the x, so I need to divide both sides by 7. These 7's will cancel out, leaving us with just x on the left side. 49 divided by 7 is 7, so my solution is 7. Okay, same thing with b. W's on the right side, no problem with that. It's being multiplied by 2, so we need to do the inverse, which is division. The 2's on the right side cancel, leaving us with 3 halves equal to W. Now, these were all what we would call one-step equations. There was only one thing you had to do to get your equation, or I'm sorry, your variable by itself. Sometimes we'll have one-step equations that have fractions involved. So a key thing that I want you to remember is that dividing is the same as multiplying by the reciprocal. And it's a very useful thing when it comes to working with fractions. So again, dividing is the same thing as multiplying by something's reciprocal. And we'll use this in equations that have fractions. Okay, for example, the reciprocal of 3/3 is 3/2. We're just basically flipping the fraction over. So let's use this to solve an equation. In example A, we have 5/9 times v. Now, we know that since there's multiplication happening here, we need to divide both sides by 5/9. Okay, well, I could divide by 5/9, but what's going to be easier is multiplying by the reciprocal of 5/9, which would be 9/5. So really, what we're going to do here is we're going to each side by 9. 5/9 and the 9/5 will cancel, leaving us with just v on the left side. On the right side, we have 35 times 9/5. Now I'm going to do a trick here. Let's do 35 over 1. You can always make a number of fraction by putting it over 1. And we're going to multiply that by 9/5. Now, I know that 35 divided by 5 is 7. So the fraction 35 over 5 can be reduced to 7 over 1. And when I these fractions, we're multiplying the numerators together. So 9 times 7, those are the two numbers in our numerator, which gives us 63. We multiply the two numbers in the denominator, 1 times 1. We get 63 over 1, which is the same as just 63. Okay, so trickier. It got a lot trickier there. All right, another example with fractions. We have 4y divided by 3. Start by rewriting that. 4y divided by 3 would be the same as 4/3 times y. And when I have it written this way, it's easier to see that to get rid of the 4/3 that's multiplying y, we need to divide by 4/3. Or we could multiply each side by the reciprocal, which is 3/4. So when we multiply by the reciprocal, the 3/3 and the 3/4 on the right side will cancel, leaving us with just y. On the left side, we have a calculation to make here. We have 5/2 times 3/4. Neither one of these fractions reduce, so what we're going to do is we're going to multiply these two fractions together by multiplying the numerators. So 5 times 3 gives us 15. And multiplying the denominators. 2 times 4 gives us 8. Okay, that fraction does not reduce, so our final answer would be y is equal to 15 over 8. So everything we've done so far has still been a one-step equation. Okay, let's look at some that have multiple steps. And honestly, most of the equations that we work with this year will require multiple steps to solve. Since there's going to be more than one step, you have to be careful about when we're performing inverse operations, we're going to undo any addition and subtraction first. Okay? We'll undo any addition and subtraction first, and then we'll follow that by undoing multiplication and division. You can kind of think of it as doing PEMDAS, your order of operations, backwards. So let's look at a couple examples here. In example A, let's go ahead and split it into two sides. We have 6 minus 2 times x. Okay, well, remember our trick for reordering these. This is really a positive 6 that's having 2x taken away from it. That would be the same as negative 2x plus 6 equal to 10. Now we're ready to isolate our variable, which is x. And remember, we want to undo any addition and subtraction first. Now, please remember, the minus that's in front of the 2x, that's a negative 2 that's being multiplied by x, so that doesn't count as subtraction. We want to get rid of the plus 6 first because 6 is being added to x. So we need to start by subtracting subtracting 6 from both sides. So if we subtract 6 from both sides, we're left with negative 2 times x equal to 4. Okay, remember, this is negative 2 times x, so if we want to get rid of the negative 2, we need to do the inverse operation, which would be division. We're going to divide both sides by negative 2. This will leave us with x is equal to negative 2, because 4 divided by negative 2 is negative 2. All right, example B. We're trying to isolate n, split our sides. N is being divided by 7. There's also a plus 2, so we're going to get rid of the addition first. So we're going to subtract 2 from each side. These cancel. We're left with n divided by 7 equal to 0. Okay? We have 0 because 2 minus 2 on the right side here gives us 0. There's nothing wrong with that. It's okay to have 0 in an equation. It doesn't mean that you have to stop. You can keep going. The last thing we want to do here is, since we have n being divided by 7, we want to multiply each side by 7. But something interesting happens here. On the left side, the 7's cancel, leaving us with just n. And on the right side, we still have 0 because 0 times any number is still 0. So our solution, our answer to this equation is actually the number 0, and there's nothing wrong with that. That's okay. I want you to go ahead and try examples C and D on your own. For example C, we're going to start by splitting the equation into two sides. We want to isolate y. The order is off a little bit here, but I want to show you something. We don't have to reorder the equation. Remember that the 7 in front of the y is being multiplied with the y. The minus 4 that's outside is being added to the 7y. Now, if I want to get rid of a minus 4 or a negative 4, I want to do the opposite, which would be adding 4. A minus 4 and a plus 4 are going to cancel each other out. So we're going to start by adding 4 to each side. That leaves us with 7y equal to 7. The 7 and the y are being multiplied. So now we can divide each side by 7. These will cancel, leaving us y is equal to, well, 7 divided by 7 is 1. And our final example here today, we have 1 minus 2/3 z is equal to 2. So again, I don't have to change the order. I can if I want to. The 1 that's out front is a positive 1. So if I want to cancel out that positive 1, I need to subtract 1 from each side. This leaves us with negative 2/3 times z equal to 2 minus 1, which is 1. Now I have multiplication between z and a fraction. So I can either divide by that fraction, negative 2/3, or I can multiply by the reciprocal, which is negative 3/2. So I'm going to multiply by the reciprocal, because I think it's easier. These will cancel, leaving us with z is equal to, well, let's think about it. 1 times anything is whatever the other number was, right? So if I have 1 times negative 3/2, my answer is just going to be negative 3/2. All right, everyone, please ask questions in class, rewind, rewatch, and let me know what I can help you with. Have a great day.